Okay.
Okay, please
Yeah,
start.
thank you. So we have heard already a number of talks about testing hadronic interaction models from accelerator data and cosmic ray experiments, which is, so to say, testing and learning about soft QCD. This talk is more exotic in that sense because what I will do, I will show you some tests about BSM physics by air shower data. So what we are looking for is actually when you take this photograph, which we have as on the web page, what we are actually looking for, let's see whether I get that to work, is air showers going in that direction. You know, on the poster it's going in the other direction. So this is the motivation search for that kind of air showers. It comes actually from the ANITA experiment, which has observed two events in upward going direction, which I will present. That gave the motivation to go to do that kind of study with the Auger detector, because we should also be able to detect upwards going air showers. And then I will compare our results with the ANITA observation, which was some additional exercise we needed to do. And then the answer is we don't observe these upgoing air showers, but then, of course, we can use that result to test BSM models, constrained BSM models from the non-observation. So here, if you don't know, that's the ANITA experiment. It's a balloon-borne experiment with a couple of radio antennas. It's flown over the Antarctica and with 48 antennas here. And it's long duration flights, high pressure balloon. And it has been flown for 22 days in 2014, 2015. And what then has been reported from the ANITA 1 and 3 run or observation is that there were, so that is ANITA, that is the Earth, and they reported the detection of two events in upward going direction in a geometry where the emergence angles were about 27 to 35 degrees. So, I mean, pretty much going upwards. And the air shower energy that they reported was on the order of 1 EeV, 10 to the 18 electron volts. And the interesting thing here is that these were not, according to ANITA, reflected events because they didn't show the polarity inversion which you expected from reflected events. So they were considered to be linearly upgoing air showers, which is then reported in these PRL papers. So why are these events called anomalous? That's simply because if you think of neutrinos, which go through the Earth, if you, however, take the cross-section of neutrinos at 10 to the 18 electron volt, then the interaction length in the Earth is about 280 kilometers, while the chord length for this geometry is 7,000 kilometers, about 5,000 to 8,000 kilometers for these two different events. Which means the probability, if you start with one extra electron volt neutrino, the probability to observe a tau, which could have induced the air shower, and that energy is very small, 5 times 10 to the minus 8, so basically non-existent. So that gave a motivation to a large number of bursts of papers. This is just only a few of those which appeared then in the literature, and they try to interpret the data in different ways. One is simply that it could perhaps be still downgoing events, but only reflected by different sublayers of the ice sheet, so that the polarity inversion didn't happen. Then it could be BSM particles, axionic cosmic rays being reflected on the ice, or Ascarian emission in the ice induced by heavy dark matter. It could be BSM particles upgoing, so through the Earth. And there's a number of those within supersymmetry, sterile neutrinos, axion quark nuggets, axions converting in the Earth, etc., etc. It could be dark matter decays into standard model particles, which are then upgoing and produce upgoing leptons, or it could be dark matter decaying into BSM particles, again, of course, upgoing, and so on and so forth. So this is just a small collection of all these different papers which appeared, coming up with specific models that could describe that observation by ANITA. So if you plot it, I mean, in a more schematic way, what these different models do is, I mean, for example, if you start with a standard model particle, say a cosmic ray of very high energy, it could interact with ordinary matter, with a certain cross-section, produce BSM particles. Of course, its energy is much beyond accelerator energies, produce BSM particles, and the BSM particles could again interact with matter to produce standard model particles, or the BSM particles could decay into standard model particles. And then, of course, you can have further generations of these kind of things, which, of course, make it then more complex. And what I will then in the end show is just, I mean, these two examples, or this example here, that you produce BSM particles which decay into standard model particles. Um, so what we had to do first, the point is that the Auger fluorescence telescopes, which is shown here, a figure, of course, are designed to measure downgoing air showers at night, and of course, you can by construction you can also measure upgoing air showers, and that is simply possible just also by the electronics, because the triggering doesn't take care about the direction of the air shower. And of course, we have to verify what the sensitivity is to upgoing air showers. And then if you want to do a quantitative comparison with ANITA, actually, there is a problem in the papers which were published. There was no flux because there was no exposure given. So there was just a report of 2 events, but you cannot make any comparison with any other experiment if you don't know what the flux has been. So we collaborated with ANITA to calculate their exposure for the 2 flights. And of course, we also calculated our exposure as well, so that we can do a quantitative comparison. So I will briefly address that. And then what we estimated from the very beginning is that because of the long data taking time of Auger, our exposure, the integrated exposure, should be much larger than that of the 2 ANITA flights. So therefore, we should be able to see that kind of events. So the key steps in the simulation, I mean, we had to develop a completely new reconstruction scheme for upgoing air showers, just to give you some ideas of what had to be done. Of course, we first need to understand the signal efficiency quantitatively. And then if we detect those showers in simulation, we need to understand and verify the reconstruction quality dependent on energy, geometry, and all these kind of things. Then we need to take care about possible background, because it's clear that there is a low flux of these particles. So we need to understand the background very well from ordinary air showers, downgoing air showers. And then we apply data cleaning. For example, there are laser events typically, because we operate lasers to verify the atmospheric conditions. And then, of course, our ideal upgoing air showers, which we, of course, don't want to have in our data sample. And all these kind of nitty-gritty things had to be done. And then when you have done all these studies, you apply proper cuts to the data in such a way that you maximize the sensitivity and reject the background at the best possible way, so that your sensitivity is the highest. And to give you one example of how background could occur. For example, if an air shower that is a telescope, if an air shower flies in that direction and lands behind the telescope, it will look like an upwards going air shower. And that is very simple to understand, because the light from that point P1 will be observed at that angle, and then the shower will propagate in that direction, and the light from P2, which is at a higher elevation angle, will be observed later, which means that shower looks like an upwards going air shower. That needs to be understood, right? So we have to reject that kind of air showers. And so we did that with doing blind analysis with 10% of the data as burn sample and optimize the cuts. And then the result is shown here. The blue curve is the signal efficiency as a function of a discrimination variable, which involves a couple of observables with the number of pixels and so on and so forth, the track quality. So the signal efficiency as a function of this discrimination variable is pretty constant, which is fine. These are the these open symbols are the burn data. That is later the full data after unblinding. And then what you expect then from cosmic rays coming at all different zenith angles, also stratospheric showers, which are very horizontal. The background from cosmic rays is that curve here, assuming e to the minus 2 or 2.7 spectrum. And then you optimize the cut, which is in this value here. And then there is still a significant signal probability, but also some backgrounds remaining, which we cannot totally avoid. And what we expected then, if we unblind the full data, is 0.27 background events. What we observed is one event, and that event has the typical features of the expected background. And this is how it looks like. So that is the background event. This is one of the what we call heat telescope, high elevation telescope. So it's just a corner clipping event with very few pixels. And that is the longitudinal profile that you will reconstruct. So what you see on the right-hand side is a simulated downgoing event landing behind the telescope, as I explained before. And that has pretty much the same feature as that event here. We can safely, I mean, of course, we did several further analysis, but that event is surely not something where we would claim that it's an upwards going air shower. So it's a typical background event. A real upgoing air shower would look like that. That is energy of 3 eV, elevation angle of 24 degrees, like what we have observed with Anita, and that is our maximum. Yeah, so that can be very well reconstructed. Now, what we then do is that we investigate our exposure as a function of energy. So we start to be sensitive above 10 to the 17 electron volts, and then the exposure increases. It's very much the same as for fluorescence telescopes in air shower experiment, as we know. So the same thing here for upgoing air showers. These are the exposures that we would expect for e to the -1, e to the -2 spectrum. But if you look at that figure here, from the non-observation, between, of course, we take into account this one event which we observe, but that we don't claim as a signal, we can derive upper limits on the flux of upgoing air showers, assuming e to the -1 or e to the -2, and that you can compare to the Anita flux after we have calculated the exposure. If that is a flux value, or if you interpret the Anita events as upper limits, which you could do as well, and then you see we are orders of magnitude lower, which means more sensitive than Anita. Which means we would have expected a couple of tens to hundreds of events to be seen in case we take that two events at face value. Now, if you want to go into more details, we look at the exposure in a two-dimensional way, because if you study BSM physics, you don't know at what height the shower would start in the atmosphere. It could, for example, tau's escaping from the ground, and then you would have this exponential decay curve. So there would be a high probability that the shower start near ground and lower probability up there. There could be BSM particles where the particles decay randomly in the atmosphere, independent from the height. So therefore, we investigate our exposure as a function of height and energy. And you see we are at low energies, not sensitive, very sensitive to showers starting very high in the atmosphere. This is the analytical calculation for Anita. However, you need to look at the absolute numbers here. For example, even at the lowest energy, our exposure is outperforms that of Anita. So therefore, at any energy, our exposure is higher than that of Anita. Now, we can test some BSM particles, and this is just to illustrate what could happen if BSM particle enters the Earth with a cross-section that is lower than that of neutrinos, because we know neutrinos would be absorbed in the Earth. So the cross-section has to be low enough so that sufficiently many BSM particles make it to the other end of the Earth and do an interaction here to produce, for example, tau's or tau neutrinos. You can do that as well. Which means the cross-section needs to be low enough. However, it has also to be high enough that sufficiently many interactions take place there close to ground so that the tau's can escape. So there are two competing effects. So if it's too small, the cross-section, then there is too few interactions here. If it's too high, the cross-section, the BSM particles will not make it to that point here. So you expect that kind of curve, the sensitivity to BSM particles as a function of the cross-section of the BSM particles, right? That is just quantitatively, it's a product, of course, of survival probability times interaction probability. And that you see already here, that the optimum is here at cross-section of 10 to the -33 to 10 to the -34, which is about 1% of the neutrino cross-section at that energy, because neutrinos don't make it through the Earth. Okay, and here is then the result for BSM particles. on the left-hand side, we assume just a cross-section, a constant cross-section as a function of energy. And here is the upper limit E squared times the BSM particles as a function of their unknown cross-section. So that is the upper limit here, 90% confidence limit. If you assume that the BSM particle would have a cross-section that scales or that has the same energy dependence as the neutrinos, then you would get that minimum here, which is at 3% of the neutrino cross-section. So that's one example. And then, of course, if you have done that, you can ask yourself, well, okay, we also have the Earth skimming channel with the surface detector array of Auger, where we have a very high sensitivity to Earth skimming neutrinos, and we can do the same study then here as well. I mean, the same kind of discussion. And here is just to show you the effective area for downgoing neutrinos and for Earth skimming neutrinos, and that's really huge. And that we can also use in that study. And the Earth skimming actually has been the dominant channel in the upper limits of the cosmogenic neutrino fluxes that we have published. And so we can make use of that analysis as well. And here you see again what I showed before, that curves here. Now what I have done here, we included tau regeneration, which can happen, of course, at high energies, just to make it more consistent. And that is now the upper limit of the, when we account also for the Earth skimming BSM particles not interacting and not producing a shower. And you see that it's orders of magnitude lower because we know that the exposure of the surface sector is much better than that of the fluorescence telescope. And it's also interesting if you compare that here, this is for comparison the cosmic ray flux at energies larger than 10 to the 17. So the BSM flux has to be 10 to the -3 at most of the cosmic ray flux at these high energies, which means if, for example, you consider a model where the cosmic rays at these high energies would produce the BSM particles by interactions in the Earth, the cross-section has to be such low that only in this 1 per mil of such events at the highest energies a BSM particle would be produced. So that you can actually come. I thought the microphone would not work anymore. You can compare that actually then also to the cosmic ray flux. Okay, and that brings me to the end. So what Auger is really it's a multi-purpose, multi-messenger observatory with 4-pi acceptance, and it's sensitive also to the ANITA anomalous events, and it's in strong tension, I would say, with ANITA. And the non-observation we can use to provide bounds on various BSM particles. Of course, we can test very many more BSM hypotheses. I just showed you one example effectively. Thank you.
Thank you very much for the very interesting report. So any questions? Please, Gupta-san.
No, very nice talk, Karl-Heinz. I just was curious, you mentioned that you also see these upward going, signal from lasers, but I thought lasers, you would know exactly when you fire,
Yes.
right?
Yes.
So that should not be constituting the background.
No, definitely not. But I mean, since we have so many laser events, typically about 100 hertz, and then if you multiply that with 10 years of operation, you come up to numbers of many orders of magnitude, and we don't want a single one there. So sometimes the veto doesn't work. I mean, or someone forgot something. So we wanted to make sure that we don't get confused by that. And therefore we apply in addition these cuts. It's just, I mean, to be safe.
Other questions? Can I have a question? So this one event is, I guess this is a mono-telescope event, right?
Say again, this one event?
One telescope event, right?
Yeah, only one telescope, exactly. That was a heat telescope just in the corner of the heat telescope, yes.
So if you have the stereo, let's say, how much the acceptance you have for going up event? That is more kinematics.
Yeah, right. I mean, stereo would be much more constraining, but also the exposure would be much lower, actually. So therefore, I mean, in principle, you could see stereo for high energies, but so we just, I mean, took the integrated exposure, also just single telescope, including stereo telescopes. Actually, the background event that we expect, I mean, is not only from showers landing behind the telescope, but also stratospheric showers, which are interesting in itself for balloon-borne experiments of the future. And actually, we will also write a paper about stratospheric showers, which we can detect that way.
Thank you very much. So other questions? Okay, please.
Regarding the systematic uncertainties with the cross-section at high energies and also the modeling of the composition of their cross, what are the order of magnitude?
Of the systematic uncertainties, I don't remember now exactly. I mean, let me say we are doing here order of magnitude studies, right? But the uncertainty I mean, we take into account the profile of the Earth, for example, for the cross-section, of course, and all these details. The orders would be, I mean, 20%, let's say, conservative, even better.
Please.
Yes. If we assume that Anita may be observed a transient event,
Yes.
would that be possible?
Yeah, of course, that is one of the baroque assumptions that you can make, that someone in some source in the sky just turns up when Anita is flying and is quiet else at any other time. And of course, I mean, that is highly unlikely to happen. But of course, that we could not exclude. That just in the week of the Anita flights, I mean, the source was there in the sky and is quiet all the other time.
I think more specifically, I was asking, did you compare also looking at that direction in a similar time? Or is there
Yeah. No, but then our instantaneous sensitivity is less than of Anita. So I mean, our higher exposure is only because we integrate over 10 years of data, but instantaneously Anita has a higher exposure. But as I said, that would be extremely lucky for Anita if sources just would appear when they are there. If sources would randomly pop up in the sky, then we would have seen that.
I imagine if there was a specific source, it's a very low rate.
Yeah.
And
Yeah,
one
but
would
then if
entertain
it
the
would
possibility, but that is a
exactly,
different
if it
analysis.
would show up randomly, then we would have seen that. But not if only 2 times in 10 years, exactly in the 2 weeks. Then we need to talk to Anita, then they have some connection to someone up there.
Okay. Okay, thank you very much again. So let's move to the online talk by the Sasha. Hello, can you hear me?
Yeah.
Okay. Could you share the slide?